If I put this picture up and asked you what this is a picture of, a lot of you would probably say that's the moon, right? Because it looks a lot like the moon. It is not the moon. It is the planet Mercury. The planet Mercury is a kind of boring gray cratered rock, much like the moon. I'm not going to talk a whole lot about Mercury. We're going to keep this video short, and I'll let some supplemental materials and YouTube videos and your textbook fill in the gaps. Here's a view of Mercury showing its craters very, very clearly. You probably already know before taking the astronomy class that Mercury is the closest planet to the Sun. It is a terrestrial planet, meaning it has a hard, rocky surface. It is about a little less than 1/3 the distance from the Earth to the Sun. So the Earth's distance to the Sun is 1 AU. Mercury is about 0.3 AU from the Sun, which means that the side of Mercury facing the Sun is very, very hot. The surface temperature on that side of Mercury is 800 degrees Fahrenheit. But because Mercury has no atmosphere to hold in that heat and distribute it from one place on the planet to the other, the far side of Mercury, the side of Mercury facing away from the Sun at any given moment, the nighttime side of Mercury, is pretty much the temperature of empty space. It is 300 degrees below 0 Fahrenheit. So the difference in temperature on the surface of Mercury from day to night, which is complicated in Mercury, we'll talk about that at the end, is more than 1,000 degrees in difference between the day side and the night side. On Earth, it gets cold at night, right? It is colder at night than in the daytime. But because we have an atmosphere that traps in heat, that difference in temperature is only 20, 30, maybe 40 degrees tops between daytime and nighttime. On Mercury, the difference is huge, because one side is exposed directly to the Sun and the other side is exposed directly to empty space, and that heat is just immediately lost. We did not have very clear pictures of Mercury until very recently. The best pictures of Mercury we had were from the Mariner 10 spacecraft, which flew by Mercury in 1975 when I was a little kid in kindergarten. It took about 7,000 images of Mercury. It also took pictures of Venus and the Earth and the Moon as it flew by. Its pictures were okay. The resolution is not great. The little squares you see are because these are individual photographs mosaicked together into a sort of patchwork, so they don't always line up exactly right. The Mariner spacecraft was part of a series of spacecraft that were sent to explore the solar system in the 1970s. Robotic space probes. There were no humans on the Mariner spacecraft, just cameras. And that was the last time we flew anything past Mercury, was 1975, until the Mercury Messenger spacecraft in the 21st century. Mercury Messenger was launched in, I have it up here in a second, 2004, and it flew by Mercury in 2008, orbited the Sun a few more times to slow down, and it actually was in orbit around the planet Mercury for about 4 years, from 2011 till 2015. We know a lot more about Mercury now than we did when I started teaching astronomy back in, say, 2000 or so. The pace at which we learn new stuff about the solar system makes it hard to keep up with astronomy. We know stuff about the planets that we didn't know when I was getting my PhD even. So we've learned a lot about Mercury just in the past 10 years or so, which is exciting for you, hard work for me. This is a picture of Mercury taken in false color, sort of combining spectroscopy with photography. You can see that different areas of the surface show up in different colors. This is indicative of different chemical compositions on the surface. You can also see lots and lots of craters, which means that Mercury gets hit by comets and asteroids and meteors all the time. Just like our moon gets hit by comets and asteroids and meteorites all the time. We will talk in a separate lecture about why it looks like Mercury and the moon get hit by way more stuff than, say, the Earth and Venus. That's actually not true. They get hit by exactly the same amount of stuff. One of the largest craters in the solar system, this kind of old, maybe even partially filled in crater called Caloris Basin, is one of the largest craters in the whole solar system. It's about the size of Alaska, and Mercury is way smaller than the Earth. So if you imagine taking Alaska and putting it on a planet that's less than half the size, it's a huge crater from a very, very large impact in Mercury's past. What did Mercury Messenger discover about the surface? One of the things you notice when you look at Mercury is that there are a lot of craters, but very few mountains. No volcanoes, which suggests that Mercury is not geologically active, that there are no plate tectonics on Mercury, that the inside is mostly solidified and not molten. This is an important thing that we will learn about objects in our solar system, that the smaller they are, the quicker they cool off. So the smaller a planet or moon is, say relative to the Earth, you know that the Earth is still like melty inside, right? The Earth, once you go down 50, 60, 100 kilometers, is partially molten. There's magma down there. That's because the Earth has not completely cooled off from its formation. And because there are processes inside the Earth, like radioactivity, that actually heat up the Earth's interior and keep it molten. But a smaller object like the moon, like Mars, like Mercury, has less internal heat. It cools off faster, and they tend to be solid further through than the Earth is. But Mercury Messenger did discover some evidence of past volcanic activity. It actually discovered that Mercury has a very tenuous, we don't use the word atmosphere because it's so thin. It's tens of thousands of times thinner than the Earth's atmosphere. The word that astronomers use is an exosphere. You can just think of it as very scattered molecules that are trapped by Mercury's atmosphere. The way nitrogen and oxygen are trapped by the Earth's atmosphere in what we call, or by the Earth's gravity in what we call an atmosphere. Mercury's gravity holds onto a very tenuous envelope of gas called an exosphere, and that exosphere actually contains traces of H2O molecules, water, which we would not expect to find on a planet that's 800 degrees Fahrenheit. We also see evidence from looking at the composition material on the surface of past outflows from volcanoes. This object on Mercury looks like it was a volcano billions of years ago. The material has in the past flown out from that volcano and covered the surface, giving it a different composition from what's underneath that past lava flow. So Mercury is not geologically active now, but it was probably geologically active in the distant past. Another thing we discovered about Mercury is there seem to be places on the surface where there is ice, frozen H2O water ice. How can that be if Mars is sometimes 800 degrees Fahrenheit? Well, if you imagine a point near the North Pole, right? At the North Pole, the light hits a planet at a very steep angle. That's why it's cold at our North Pole, right? Because the sunlight is hitting the Earth at a very spread out angle. Imagine a crater near the North Pole. You can imagine a crater near the North Pole where the sun is coming at such an angle so that the bottom of that crater never gets hit by sunlight. No matter how Mercury spins on its axis, a crater near the pole, the bottom of that crater could always be in shadow, meaning it's always going to be 300 degrees below 0 Fahrenheit. We have found craters on Mercury that seem to have water ice on the surface in the shade that never ever gets heated up and evaporated by the sun. This is exciting, not because we think there's living creatures in the water on Mercury. There almost certainly isn't. But it's exciting whenever we find water anywhere in the solar system because we think of water as being an essential ingredient for life. So the more water we find in more different places, the more confident we are that water is relatively common in the solar system and in the universe, and planets with water on them are not particularly rare. What else? If we look inside Mercury, and how do we do that? We get a map of the inside of Mercury that looks something like this. The crust of Mercury is between 100 and 200 kilometers thick. That is way thicker than the crust of the Earth. The crust of the Earth is only 8 to 25 kilometers thick. So the crust of Mercury is 10 to maybe 100 times thicker in places than the Earth, despite the fact that the planet is smaller. Why is that? Because it's smaller and it has cooled off more than the Earth, so it is solidified more than the Earth. Below the crust, you have a semi-molten mantle, and like all terrestrial planets, Mercury has a core that is more dense than the crust. Earth has a core that's made of heavy metals like iron and nickel. All the terrestrial planets have a heavy, dense core. But Mercury's core is bigger than we would expect it to be for such a little planet. Relative to the size of the planet, Mercury has a really, really big core. Now, how do we know this? We have flown spacecraft past Mercury, right? From the gravitational pull that spacecraft feels as it orbits Mercury, we know Mercury's mass, because mass is what causes gravity. So because we have orbited a spacecraft around Mercury, we know what its mass is. We can just look at it and tell what its size is, so we know what its density is. And we know the density of Mercury is way bigger than the density of rocks, which means inside of Mercury, there must be something that's more dense than rock, like a metallic core. This is how we figure out the internal compositions of planets. So why does Mercury have such a big core? One of our guesses is that while Mercury was forming, it was bigger than it is now, maybe as big as the planet Mars. And during the process of forming, it got whacked by a large comet or maybe even another planet that was in the process of forming, and that collision knocked off a bunch of material that should have been the rest of Mercury. It should have more mantle and more crust, but it got smacked early on in its formation, leaving behind a core that was larger than we would expect it to be. That's one model. Is it speculative? Sure. But that's our best guess to why Mercury looks the way it does inside. So that's our explanation for why there's a big core. Mercury's orbit is notable because it is very eccentric compared to the other planets in the solar system. In other words, the ellipticalness of the orbit, it's the departure from being a perfect circle, is pretty big. When it is at aphelion, which is the furthest point from the sun, it's about 1.5 times further from the sun than when it's at perihelion. So for the Earth, this distance is a couple percent. For Mercury, it's about a factor of 50%, which means that Mercury's orbit is interesting, and it means that some of the orbital effects on a planet are exaggerated for Mercury. One of those effects is the tidal force. When we talk about the Earth and the Moon, we talk about the tides as the moon exerts a force on the Earth that's stronger on the near side than the far side, and that causes the oceans to get stretched out, and that causes the phenomena, what we think of as tides, is the water being deeper during part of the day than the other part of the day. That's caused by the moon's force of gravity stretching the Earth's oceans. The planet Mercury is so close to the sun that the sun causes tides on the crust of Mercury. It actually stretches Mercury. And this has had an interesting effect on the planet's rotation. Mercury goes around the sun every 80-some days. Mercury also spins on its axis, just like the Earth spins on its axis every day. So a trip around the sun is called a year. A rotation on the axis is called a day, right, for Earth. Mercury's rotation and its revolution are locked together in what's called a resonance. Mercury rotates on its axis 3 times every 2 times it orbits the sun. So that means there's 3 days every 2 years. It's really hard to picture. If you were on the surface of Mercury looking at the sun, you would see 1 sunrise and 1 sunset every 2 orbits. The reason for this mathematical relationship is not a coincidence. It's because the tidal force that the sun exerts on Mercury has slowed down its rotation to the point where its rotation and its revolution are locked. They're not locked in a 1-to-1 ratio. Our moon is tidally locked to its orbit in a 1-to-1 ratio. The reason we always see the same side of the moon is because the moon spins on its axis once every time it orbits the Earth once. That tidal locking is caused by the tidal forces between the Earth and the moon that have slowed the moon's rotation. That 1-to-1 tidal resonance is a stronger tidal resonance than the 3-to-2 tidal resonance that has slowed the orbit of Mercury. The reason this happens to Mercury and not to Venus, Earth, and Mars is because Mercury is very, very close to the sun. The tidal force that it experiences due to the sun stretching one side of it is much greater than experienced by any other planet. This tidal locking means that if we imagine a habitable planet this close to a star, okay, or a potentially habitable planet this close to the star, can we imagine a planet that is daytime for 100 days and nighttime for 100 days and facing the sun for 100 days and facing away from the sun for 100 days? What would that do to the weather? What would that do to the habitability of a planet? File this phenomenon away, the phenomenon of tidal locking. Put it in the back of your head, that if you're very close to a star, you can wind up with your rotation and your revolution weirdly synchronized to one another. Because this has implications for the habitability of planets that might find themselves very, very close to their star. And why would we be interested in a planet very, very close to a star? Isn't it too hot if you're very, very close to your star? Well, not necessarily. Remember when we talked about the HR diagram and the abundance of different types of stars, the most common stars are K and M stars, stars that are smaller, less massive, cooler, and dimmer than our sun. So most of the stars in the galaxy are small, cool, dim. It's possible to imagine a planet in a habitable zone around an M-class star that is as close to its star as Mercury is to our sun, because that star is cooler. And so instead of being 800 degrees, the surface temperature of that planet might only be 200 degrees or 150 degrees. But is it possible to imagine a planet in the habitable zone of an M-type star that doesn't get tidally locked in this weird way that they're only 1 day every 2 years, or 2 days every 1 year, or 1 day every year? If it's exactly tidally locked, the day and the year would be the same. That means there would be one side of the planet that never ever got sunlight. Can we imagine a habitable planet in such a situation? It's hard to. So, like I said, when we talk about exoplanets and extraterrestrial life and habitability, file this phenomenon of tidal locking away, and we'll come back to it. So that's all I'm going to say about Mercury. I'm going to let other videos and other books fill in some of the gaps, and then we'll move on through Venus and on outward through the solar system, one planet at a time.